Okay, so today let's look at the course project. Hopefully, I can use 2 lectures to get it done. I actually, since I already told you guys, we had a version. One of the students have put everything together in the past summer and made a functioning ADC in LT Spice using the 50 nanometer technology from Dr. Baker's textbook, from our textbook. Um, and I found some little issues. It's pretty much okay. I found some little issues, and I started trying to fix these issues in a huge folder. And I just found out if I change one block here, I have to change some of the sub modules as well. And um, you know, some of the NAND gates are used for SAR, some are used for a different component. They are very similar but different subcells. So I ended up spending like the whole day while I was replying to Kelvin, but I was working on LT Spice like entire day. I didn't do anything. Um, so I think if this took me one day to do nothing, just working on this one, probably gonna take you guys a week since you have other courses to work on, right? So expect to work on this for a week or so as a course project. Okay, everything is done. I already submitted all the LT Spice files. Download can be downloaded here. So if you click it, okay, can download that zip file. Has all the subcells, everything, but in LT Spice. So I'm asking you guys to duplicate the work in electrical VLSI using C5, not using the 50 nanometer technology, which is 1 volt. So I use the 1 volt for 50 nanometer technology because it can only handle 1 volt, and the threshold voltage is somewhere around 0.3 volts. If we use electrical VLSI, we have to use C5 because there's no such a technology or PDK can, PDK is precise design kit. Whenever you are working on a new technology, you have to install PDK to a software called Cadence, which is ridiculous. We started working on that for our senior SEM team. It's been how many months? Like 2 months already, and still trying to configure that software, the EDA design environment. I mean, we just couldn't even start laying out all the circuits. Isn't that ridiculous? I mean, just hopefully in the future, like there's something like LT Spice, we can directly just double click and open it up and load the PDK and start doing laying out, like electrical VLSI. Yes, everyone uses Cadence in the industry, but I just don't know why. Is that because the cost will be super high or something? But all these companies, they're super wealthy. I mean, if you look at their stock price, billions of dollars. But I just don't know why they cannot make it user friendly. Whenever you are installing a new PDK, it takes a month just trying to debug the issues in Linux. And in all the companies like Qualcomm, Intel, they may have more than one. But for smaller companies who are making integrated circuit design, they have to hire a full-time person, like pay that person $80,000 a year just sitting in a little room to configure or manage that server or debug all the issues of the tools. So anyway, whenever you are trying to use a new PDK, you have to install it to Cadence in order to use it. Because we do not have electrical VLSI does not allow you to install any Cadence, any like TSMC 180, like the most modern technologies to electrical VLSI. No, you can only use the C5 or the 300 nanometer scaler, the scale. We are using 300 nanometer as 1. And the minimum size will be 2, which is 2 times 300 nanometers, which is 600 nanometer. But C5 means 500 nanometer technology, but doesn't mean 500 nanometer will be the smallest size you can use. So the yield will be low if you use 500 nanometer as a minimum size. So we use 600 nanometer, which is 300 times 2. So that's why the minimum size of the length of the transistors are 2 minimum. You have never seen 1, right? Have you ever seen 1 somewhere? No. If I write a 10 to 1, it's not a scale. It's a 10 versus 1 micron. So 1 micron is still 2 times 500, right? So, anyway, so it's going to be 2 as a minimum for C5. So that's why, I put everything in LT Spice and simulated using 50 nanometer technology because is this boring or is this complicated? It's just like whenever you're designing a integrated circuit, you have to put everything in consideration. Like, why do I use 50 nanometer technology, which is a not fabricatable model from Dr. Baker's book, for this verification? Because this 50 nanometer technology is a 1 volt technology, and the one we are going to fabricate using the cadence server and also the TSMC 180, which is fabricatable, which is the second most popular, technology on this planet so far, is a 1 point something volts. It's very similar to this 15 nanometer. If we use 5 volts, then it's going to be a too much difference. So that's why I have to use 50 nanometer technology for verification. So that's why everything has been built in 15 nanometer technology, which is a model file you can download. It's also included in here. However, for educational purpose, since we haven't gotten that cadence server configured with that up-to-date PDK 180 nanometer technology, that's why for educational purpose, you have to keep using electrical VLSI under C5, because C5 is the only thing we can use on electrical VLSI. So, but I'm not going to ask you guys to do the layout this semester. It's going to kill you guys. So let's just do schematic. And it's very doable. I'm not asking for unreasonable projects, right? It's going to be a lot of work, but doable. So everything has been done in LT Spice, and you cannot directly copy and paste to electrical VLSI because they're not compatible in that way. So still have to design every single digital block in electrical VLSI and do DRC, no LVS because there's no layout, right? Only DRC check and run simulation. Yes, so the simulation is going to open up LT Spice and run the simulation, but the schematic are not drawn in LT Spice. So I'm asking you guys, since I'm going to take points off, if your the organization of the libraries are just everywhere, it's just super messy, because I'm gonna pick up one or more than one of your electrical VLSI libraries and directly give them to next year the students who are taking this class, so they can start from there and doing the layout. So you are not getting killed; they are getting killed. If they will be, I mean, I don't know how. It's gonna be a lot of work, I can tell. But that will be a really good experience. But if you think like you have enough energy, you want to do the layout and the schematic, go ahead and do it. You are more than welcome to do it. Think about that. If you put this on your resume, right? We are not. I spent a few minutes in the weekend to try to find out the foundry who can fabricate that C5 design for us, and I didn't find anyone. So Moses, which is a company, was doing this kind of fabrication for free. That's why I did it for my analog class 3 years ago, just once, and then 2 years later they just discontinued that service. And the minimum amount of order for the 500 nanometer technology, which is a 60-year technology, still $20,000 with Moses, and the service is pretty great since I'm recording. Anyway, so I'm not going to do any business with them anymore in the future. So that's why we found out Muse Semiconductor, based in Colorado, and they are able to do that 180 for $5,000, a little bit more than that, probably, um, on a 5 square millimeter die. So that's why our senior SAM team is doing that right now. Okay, that's the only affordable way we can fabricate any IC chips for our students in the US, or probably on this planet by far. Um, they definitely need to improve it in the future. But I'm not the person sitting in the office, so I cannot get any executive orders to push this or give more funds to this kind of practice. Anyway, so we just do whatever we can. Um, so which means we are not going to, for the students take this class in next year, they are not going to fabricate that ADC under the 500 nanometer technology. But as long as we have the schematic and layout there, it's ready. Whenever there's a chance, I'm going to send it out for fabrication. So we can have a 5 volts version and 1 volt version for the ADC. And we're going to improve it in the future as well. So it's just keep adding to it, not just trying to get one, a complete version done at one time. So starting with a very fundamental ADC, and then add a serial communication port to it, and then add a CPU to it, just make all the connections, but have to start with taking baby steps. Just make sure this works first, and then next step, right? So yeah, so that's the whole background. That's a big picture of my thoughts regarding this program. And students have been, one student asked me last week, asking about the computer engineering program. Are we directing this major into an electrical engineering direction because we are all electrical engineers? So the answer is no, because since you haven't been in that electrical and computer engineering department in a bigger institution, I have been in there for many years. So curriculum-wise, electrical engineering and computer engineering, they have more than 80% overlap in their courses. And for electrical engineers, they have several options, several concentrations. And computer engineering is one of the concentrations in electrical engineering. So you can pick up a digital, voltages and currents, right? They're electrical engineering. Whenever you don't have any intermediate voltages, it's digital. So it's still electrical engineering, but in the digital domain. So there are several concentrations for electrical engineering, and I think the computer engineering concentration is the best or the most popular concentration in electrical engineering in the big field. And so the courses computer engineering majors are not taking in the double E major, are something like signal and processing, so it's not required. It's useful but super boring, and electromagnetics, so it's not required, and communication is required for electrical but not required in digital. It used to be very popular, but not right now. And a few other courses you can tell. So the reason I'm trying to say that CE or in other institutions called CPE is more popular than double E is because the double E still covers a lot of really old technologies to build on the, using either high power or high voltages built on the breadboards, makes things pretty big. But for CPE or CE, it focuses on the small voltage or low voltage stuff like 5 volts, 3.0 volts, even 1.8 volts. These electrical components are being built on CPUs or silicon dies, so they cannot handle high voltages and they can run faster. That's why this is more popular right now. And yes, it's definitely different from the CI's major, computer science. But for students here, they learn, for CS, yeah, you may have more than one algorithm classes. We only have one. So that's one of the weaknesses over here. But it's not a CS major anyway. But I'm talking with other professors trying to add more software courses to it, probably algorithm 2 or something. So the C students can have a stronger background in the future on programming side. Anyway, I mean, it's all very good stuff. You know, if you work hard, I think it's very easy to get a job in the future. And the pay will be really good. Okay, so let's take a look at the course project now. I reorganized everything and luckily it worked at the first time. Otherwise, it's gonna take me like another day to debug it. So which means it's not really difficult. Okay, sample and hold, a comparator, a star block, R2R deck, and a register, parallel in, parallel out register, and a timing diagram. So first, the sample and hold. Okay, you know, have to understand it first. So the purpose of before we move to here, we have to run some of the simulations first. Okay, let's look at this one. It's a sine wave with a cap. So what is VL? What VL looks like? This is the weird circuit. It's helping you guys to understand what's going on for the charge pumps. Okay, but now let's just look at this one. So AC can pass. So cap or AC signal can pass a cap. Right? What does that mean? It's a short circuit. It's a cap, yes, but VL is going to copy V in. Is there any time delay? Any time delay? No. Why? The charges are moving in the speed of light, instantaneously charging up the cap. And why, when you add a resistor there, it has a delay? Because the resistor limits the current. Okay. But this one, there's no resistance. IDOA, there's no resistance. So whatever voltage here is going to appear here immediately. Because this is the AC, so whenever it's charging up this side of the plate, it forms an electric field. And what's happening here for this one? It's pushing, so the positive charges are accumulating here, and it's pushing or expelling the positive charges on the other side as well. So the charges are moving. So whenever it's AC, the electric field will make the connection from here to here indirectly. But if you simulate it, V in, so what does V out look like? Same. Okay, keep in mind. Have you seen this in the past in circuit one or something somewhere? I mean, using LT-Spice is really convenient. So you can, verify some ideas really quickly. You don't have to go to the lab and build a circuit on the board. And also all the components on the board are not ideal. So whenever you are looking at the results, it's actually confusing you. It's better to run simulations first. All right, second one. So what does this mean? I mean, if you look at sine wave, DC offside is 0, amplitude is 5, frequency is 100. If I run the simulation, so it's a sine wave. So 5 volts here is the amplitude. Amplitude means from here to here, not the peak to peak amplitude, right? So it's the sine wave swings around which voltage with a 5 volts amplitude? 0, right? And the other side of the source is grounded. Okay. So what do we expect over here and why? So let's see. Whenever this, for example, I just started this, just open it up, right? The source. start charging up the cap, right? Start charging up the cap. Since we know the cap is going to pass AC, so this node is going to be charged up as well, right? So it's going to go up. It's going to track the input until 5 volts. Whenever it starts falling, what's going to happen? So whenever it starts falling, so for these two nodes, I mean, this one has gone up to 5 volts, right? Before it starts falling. So 5 volts is really the highest voltage it can have. So what's next, though? So the voltage here is not able to be discharged to the ground because this diode is going to block it. All right, so the charges will stay there, has nowhere to escape. But however, whenever this one, I mean, after several cycles, for example, the lowest voltage on the other side of the diode is 0 volts. So is that possible that the voltage here goes down, goes lower than 0 volts? Why? You make a case, right? Think about it. If it is lower than 0 volts, what's going to happen? No, when there is lower than 0 volts, for example, the diode is ideal right now. Okay, the diode is ideal, just blocking the current runs in one direction. So whenever the voltage here is lower than 0, lower than here, since here is permanently 0 volts, whenever here is lower, the ground is gonna dump current into this node and pull it down to ground again. So it's gonna be either 0 or up. Okay. However, so the lowest voltage here is 0. Okay, that's a conclusion for now. Because this voltage is pretty definitive, we make it 5 volts and it's going to be 10 volts VPP. It's going to be 10 volts VPP. And whenever it charges up to this cap, it has to be, it's going to add a voltage difference across the cap, no matter what, because it's very strong voltage source. Whenever it's charging it up, it's charges it up. So that means the lowest voltage here becomes 0, not -5 anymore. So it has to go up to 10 volts. So what is like the first time it charges this guy to 5 volts, and the next time it's gonna go up based on that 5 volts. It's gonna step up. The charges has no place to go. Cannot discharge it through to the ground. So just the DC off side will be moved up by 2.5 volts. By 5 volts, sorry, by 5 volts. Okay, and this is called a voltage doubler. But the thing is, it's not done yet. All right, after the voltage here has been shifted up, let's look at the next one. So here's still the voltage doubler structure, and here's the regulator, half wave regulator. So it's going to smooth out that all the oscillations and make a DC into a DC, very close to DC, not really, but see V in, V out shifted up, and the final output, like a DC voltage. Yeah, it won't be done in one cycle. It's going to start charging up. So whenever all this cap is full as well, right? So it's becomes stable. But the thing is, just this structure here, It's a half wave regulator. It's going to smooth out that AC oscillation and make it into a DC voltage. That's how it works for your, for all these adapters, DC adapters. Because right now we are trying to make a high voltage power supply. You don't have to make it high. You can directly just use a rectifier, right? And it's going to be the whatever the voltage here. So whenever it rectifies it, it's just tracking the top voltage here, right? Just smoothing out the oscillation over here, but it's not giving you a high DC voltage. So that's why I was looking at the website over here. There's a company called Voltage Multipliers, right? It's the high voltage solution, providing all those high voltage solutions. You want to, buy all those modules. Probably they have a voltage multiplier in there. So I'm going to show you that circuit, which is based on the voltage doubler. You can raise the voltage to thousands of volts, like 2,000 volts, by adding many stages. So this one was just doubled, right? Not exactly, but very close. You can look at this voltage here. It's 8.8. It's not 10, but 8.8. There are some losses from the diodes. Okay, you want to double it first, and then filter it out to remove all the AC components. And next, so this part is still the same structure, but I'm using the shifted AC here as an input for the next stage. And here as a DC baseline instead of 0, because this part has been smoothed out or rectified, right? So you have a higher DC baseline and a higher AC, so you can further increase the output. So V in, here's the first shifted signal, and here's the second. Here's the second shifted signal, and the right one will be the final DC output. Does that make sense? So this structure, if you look at the circuit, this structure will shift the AC up. However, remember this part. So in the first stage, the lowest voltage, DC voltage for here will be 0 volts, right? We just talked about that, because whenever this is lower than 0, the ground is gonna dump current into this node and make it 0 again, right? So that's why it lifts the DC voltage, lowest DC voltage at this point, from -5 to 0. And the same concept for here. So it lifts the lowest DC voltage from 5 to 10. So now it's the lowest DC here will be 10, and everything will be built up upon that DC voltage. And then it's being rectified. So you got V out. And you can keep adding these stages to it, so you can get a pretty high DC voltage, 2,000 volts. You can just build everything on breadboard, just have all the caps and dowels, high voltage versions, so those are not being blown up. Just build a few stages, like 10, 12 stages, you can get 2,000 volts. You can even see it, like whenever you turn it on, after a while, if you place that two metal pins close to each other, it's going to break through the air. You can see the sparks. Pretty high voltage, 2,000 volts. You can build it in lab. Be careful. Okay. It's the same circuit, but just in a different view. I cannot rotate the components by 45 degrees, but just show you guys. You may see a similar structure somewhere else. It's the same circuit. I just rotate it and place it in different locations. It's the same as the one I just showed you guys, but more with more stages. I just keep adding more stages. You can, do even more. Look at that. So here, a cap, a diode, right? So that's a voltage doubler. And then from here, a diode and cap. So that's the rectifier. Okay, same concept here. And if I run it, you can see V in is this one. I mean, couldn't even see. It's a lot of sine waves. And V out is here. 70 something volts, right? Just keep adding more stages. Probably can get a few hundred volts. Okay, just show you guys these things because this part, okay, is a charge pump. So the sample and hold circuit, the purpose of that part of the circuit is to, see here, is to sample and hold at that DC level. So the clock, the blue one, so first is the black sine wave is V in, right? It's just data, like sine wave, for example. And then clock are these spikes. So wondering like why they are not 50% duty cycle. The clock usually they have the same width and length, same width for the on and off times, but this one why is not? So that's why it's critical to understand the timing. But when you are looking at this entire diagram, so the most difficult part will be this clock, this timing circuit. The timing circuit defines at or during which time period to let the circuit to do what. It's the brain of the ADC. I have to design this one first to make sure you know what you're doing. So this one is like a commander, right? It's sending all the commands for the other circuits. So that's why, if you zoom in here, so I just grab one of them and I zoomed in, you can see what's going on here. So the clock of the sample and hold circuit, it samples, see at the rising edge, it samples. The black line here is the sine wave, part of the sine wave, all right? So the clock sampled it. Why? Because you can see the output, which is the right line. The reason it's sampled because you can see after that rising edge, the red line was here, but now it's going up to trying to track. So it's sampled and then start tracking. How can I tell it's tracking? The right one and the black one are overlapping to each other, right? So you cannot see the red line anymore. It's tracking. Okay, after the track, it starts holding that voltage value. So that voltage point, which point? Actually, right before, so the voltage dot. Look at the black line, which is the V in. So that little data point, right before the falling edge of the clock, that point is being sampled. Because afterwards, it's going to be the same voltage. It's a flat DC line. It's being held at that voltage. So why I want to hold it there? Why I want to hold it? So analog signals are continuous signals, like the sine wave. You can see the black line here, right? But you want to digitize it. What does that mean? Digitize it. You sample, boom, boom, boom. Sample it really frequently, and then you can recover the sine wave. But actually, you are not. You are losing points. Are you losing points? Yes. See all these points? All these sine waves are being lost. You're not sampling these at all, which is fine. You're not getting infinite resolution for any ADCs. All right. So why I want to hold it for a while? Yeah. Do you remember that how many states do you need to complete the star conversion? If it's an 8-bit, how many states do you need? No, 8-bit SAR. Remember I give you, for example, it's a 5 volts. No, it's a 10 volts VREF, and I have an input at 6.2 volts. And they're comparing with 5 volts at the very beginning because the initial state will be 1, 0, 0, 0, 7 zeros, right? And that one's 5 volts. And I compare 5 to 6.2 first, and it's apparently smaller than 6.2, so the comparator's output will be 1. Remember? How many states, how many circles do you need? Yeah, n plus 1. So for 4-bit, for 3-bit, you did on your homework. How many states did you draw there to complete the whole conversion? 4. For 4-bit, which you did in your midterm exam, how many states do you need? 5. For 8-bit, how many states do you need? 9. Okay, so you need 9 clock cycles to get it done, to have that data ready. And then you need the 10th cycle to send it out. Takes time. Like boom, 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 right? So it takes time. That's why you need the data to be held here, to make that happen. So in that case, you can use a 50% duty cycle clock. It's not making sense. Why? After this data is sampled, I just want to make this narrow because I just want to sample it. I don't want to take the time to do the conversion. So I'm saving time. Whenever you can sample it really quickly and then do the conversion, so actually reducing the entire period for each cycle. So you can run the ADC at a faster rate. So 50% duty cycle is going to work, but it's bad. And I think this one can be narrower, even narrower, actually. And see, it tracked the input for a while, right? For like how long? Like 1 microseconds, right? And which is totally unnecessary. I just need to boom, sample, done. I just want to sample it really quick. Okay, so we need a sample and hold circuit for that purpose. And here's how the circuit is designed. So this was from this author's paper. And if you click it, there's a full text of it. And one thing I want to mention, since definitely you can find out the circuit, the schematic of the circuit over here. Right, this one. Something I wanted the senior SAM team like Noah is on the team to know is if you look at other figures and other explanations, probably will help your project as well. I just found out like the op-amp, it's already there. But there's still a lot of time to find out some other circuits, schematics. So this one probably will work, even including the biasing circuit here. Anyway, so you can read the paper for explanation, but however, I'm going to explain to you guys in the version that which is, I think, better, more intuitive. Yeah, since we studied the paper and digest it, right, and then trying to tell you like how that works. Okay, so now let's take a look at this one. Clock. Which is a clock of the sample hold or not? Yes, right? See, I made it into a box, and this clock is definitely this clock. Okay. Right. Okay. A quick question. when you want to make that type of clock, so the ADC chip, you have never used it, but for example, I give you an IC chip, right? It has a clock pin over there. And you can connect it to the Arduino's clock pin. So it's actually giving oscillation to it. But that clock pin won't be like something like this, right? It's not customizable. It's going to be a 50% duty cycle. How that works. You have to make the sample and hold clock yourself. How many clock sources you may have when you are interfacing your digital system with any ADCs or any other components you can buy the off-the-shelf ICs. Usually there's only one. They're not going to like have a data sheet and telling you, for the company who are selling the ADC chip and telling you like, I need a 15% duty cycle clock and a 25% duty cycle clock and a 35% duty cycle clock, and they have to be aligned in that way. And then you feed the clock to the ADC, it's going to work. No one's going to buy that. Too complicated. I just have one 50% duty cycle clock and do it. You can do it, cannot do it. I'm not going to buy your chip. Make sense? You're not going to like modify and making all these, clocks trying to make that ADC work. It's too much of work. All right. You can use a counter, like just one clock source, and the counter is gonna make a pulse after several counts. Can you? Yes, the timing circuit. That's how that works. The counter circuit, you don't have to redesign it. It's already there. It's counting from 0000. Four bits will be 0000 until 1111 and then come back. However, I need it to come back to 0 whenever it comes to 10. Why 10? I need 9 cycles to do what? To do the ADC conversion, to run the SAR algorithm. I need 1 actual cycle to send it out. So I need 10 cycles. So I need this counter to count until 10. So I have original clock, which is pretty fast, right? And I'm going to use, keep in mind, one source clock always. When you are designing the circuit, you just imagine there is only one, for example here, 2 megahertz clock running. And whenever it comes to 10, do it. Does that make sense? So you can imagine the duty cycle here will be like 20% or so. I mean, 10% actually, right? Because 10, 1, 10, 1, like less than 10%. Because you have 11 on time ons and 1 is really on. All the other 10s are actually off. So that's why the clock looks like this, because the original clock is always oscillating in between, but only give you a rising edge after it comes to 10. Okay, that's the clock you should use for the sample and hold circuit. So here's a clock. Here's a clock knot. Here's a clock knot. You have to look at the clock first. Whenever you are seeing a circuit like this, you have to look at the clock first. So clock, inverted clock knot. Clock knot, clock, all right? This part of the circuit, probably I should ask Noah to explain this. He can do a better job. I'm kidding. All right, so the purpose of this line here is to provide a high gate voltage to this transistor. Don't get scared by this part of the circuit. It's doing very simple task. It just looks complicated, but actually it's not. So everything here is doing nothing but provide a 2 VDD voltage to this part. why you want a 2 VDD to the gate here? So V high is being shorted to VDD in the future. And I need a higher VDD. Why do I prefer a higher VDD, higher gate voltage? You know, can be 2 VDD, can be a little bit less than 2 VDD, which doesn't matter. I just want to lift that gate voltage. So this NMOS is going to pass, since I want to pass the VDD signal to the terminal here, I want to pass the VDD to here. If you only have a VDD, your VGS is going to be 0, right? If I have a VDD here and you pass VDD here, then VGS becomes 0. So which means you can never pass the VDD from here to here if you only turn it on at VDD. So the voltage here will be VDD minus VTHN as the largest. So you want to turn on this more. So that's why you need a higher voltage. And this part of the circuit is a charge pump. It's going to provide a higher voltage. Similar way as the one I just saw, the voltage doubler, okay? Use the cap. And the cap, the voltage here, the charges here has no place to escape. It's going to accumulate over there. So it's getting a high voltage to this point. Okay, so I'm dividing this complex problem into individual ones. So we are not looking at the details of the charge pump now, but I just need to know whatever here is doing is just provide a 2 VDD to this point. Okay, that's the starting point. Forget about everything, just don't look at it. 2 VDD is going to pass VDD to here. Whenever it passes VDD to here, at the same time, this NMOS is on, so it's discharging the other side of the plate to ground. So which means it's like you have a voltage source on the top to dump charges to the cap here, and the other side is going to pull charges down to ground. So it's going to have a VDD voltage drop across the cap during that process. It's like a cap here, right? So during that cycle, on the top, it's going to dump water to the cap, and at the bottom, I'm going to connect to ground. So whenever it's dumping charges, here it's like pulling charges to the ground at the same time. Just during that little opening, really short opening. You can just imagine there's something flowing from the top, water or some charges. I know you cannot see it, but just imagine there's something like doing this. And after that, because this one is controlled by the gate, right? After that cycle, so this one has some, during the other cycle, this will be off, and this will be off as well at the same time. So which means after it dumps that charges to the cap and make a VDD electric field across the 2 plates of the cap, and then disconnect it, what's going to happen? So I have a cap, right? It's going to dump charges to it as a lot of charge, and then disconnect the 2 terminals. What's going to happen to the plate? 2 plates. It's like a floating VDD over there. So the charges have no place to go. So the 2 charges are like a battery with the charges stored from the previous cycle, and then it's ready to be supplied to the next stage over here. Okay. So what this circuit does, it has a floating VDD over here, and then what's going to happen is here is a sample in, which is a V in, is a sine wave voltage in, the voltage in, and this transistor will be on. Don't worry about why it's on, but it's on. So this V in will be added to here. Remember, it's still the same concept. You already have a VDD across the cap. All right, but this voltage in is trying to dump more charges to here. So what's going to happen to this point? So the charge on the caps has no place to go. Keep in mind, it's already disconnected from the top and bottom, like a floating VDD over here. And now, so floating VDD right now means because it was dragged to the ground. So imagine that it's VDD and 0 volts. Okay? And you cannot change it. It has no place to go. You cannot change it. It's always VDD and 0. It's a VDD drop. The amount of voltage drop will be VDD. And now I'm adding something to here, like AC signals. AC is going to pass to the other side, right? But is it able to change the voltage across the cap? No, it's not changing it. But what's going to happen is that AC voltage, which is actually the signal, will be added to the VDD on the top. So like a VDD DC voltage on the top plus that AC swing. So no matter what the V in is, the voltage here will be V in plus VDD. Similar to the voltage divider, voltage doubler I just showed you guys. It has a base voltage here stored over here, like VDD DC, and then it's adding that V in. So it's gonna, so this will fluctuate based on the V in signal, right? It's gonna be the same shape. So the purpose of that one is, if you look at the signal here, so that's the last stage of the sampling transistor. Okay, I'm going to show you that one just to tell you like where is that. But however, the purpose of that one is, since it's changing from, it's going to track the same variation of the sine wave, but the DC voltage difference across the two capacitor plates are not changing. So you are getting a constant VDD difference across the cap, no matter what the input voltage is. It's going to follow that pattern. All right. So the reason we want to do that is for the last stage over here, we're going to keep the VGS to be a constant as a pass gate. We don't want to change it because you can imagine, like, if we just connect the gate of this stage on, because this is the last stage, I mean, whenever the voltage in changes, VGS changes. If you just keep this to V high, V or VDD. Is that correct? It's VG, VS, right? So when VS changes, if you just turn it on using VDD, then your VGS changes. Yes, this voltage will be passed to here through this pass gate, but it's not ideal because of the change of the VGS. And why it's not ideal? And we're still studying that, right? So refer to the paper, but just keep in mind, what is desired is, you hope, if you look at this model here, for the NMOS, we hope the VGS to be constantly VDD, not the VG to be VDD, but VGS to be VDD. So we are turning on the NMOS at the same level always. It's just a model, right? You just want to make it happen using all the circuits. So this is just the model, and this is how you implement it. So you are turning on VGS here using a constant VGS. How? This. And why? It worked out because you can look at that. VGS here is constantly VDD. Always, no matter what the signal is. It's always VDD. That's desired. Okay? So that's the big picture of this sample hole circuit, and we are going to talk about the clocks, like when it's going to do what on Wednesday, all right? And there are many other components as well. I want to explain to you guys so you understand it, all right? Okay, I'll see you on Wednesday.